So last week kind of took a bit of a break from that low-level AWS stuff and looked at what I call application architecture. And I want to finish those slides this morning with you. And then we'll go back to talking about some detailed AWS stuff, looking at some new services, which would also be classified as serverless, even though they predate the serverless kind of model. So, in terms of labs this week, I don't have a lab for this week, so the assumption is that you'll be working on the assignment, I guess. So I'm going to start off revisiting this set of slides, as I said, and trying to pick up the story. We got through most of it. It's heavy enough going. Often when you're discussing kind of high level issues, it can be a bit abstract. But the general gist of it, if you remember, was we started off by talking about this idea that in modern day software development, we as software engineers have to be able to produce applications rapidly, frequently, and reliably. Frequently, in the sense that we need to be able to adapt an application, either add new features, modify existing features, but we need to kind of turn them around, so to speak, as quickly as possible because our customers or clients, they are operating in an environment that is also rapidly changing. And so they want their software applications to be able to keep up with the changing pace, I guess. And I then said that if you, as a software house or a software engineering team, if you want to be able to meet these kind of requirements of rapidly, frequently, reliably producing software, then the ingredients, if you like, are a combination of choosing the right architecture for that application, having the right software development process, and thirdly, organizing your software development team appropriately. Now, our focus was on the architecture, which is the bottom right-hand corner of this triangle. We know a lot about the process from the Agile module last semester. And the key thing about organization, the bottom left there, is that your overall software engineering group should be broken up into smaller subgroups or smaller teams where each subgroup or each team is responsible for just one part of the application, ideally. And then, and also that subgroup, we would like them to be autonomous, meaning that they could change their particular part of the application without concerning themselves about the rest of the software engineering group. That's the ideal world. I then just said that, okay, so our objective is to, well, we focused in on the architecture side because we know a lot about process, and there isn't much more I can say about organization over and above what I've just mentioned there this minute. But in terms of application architecture, to try and identify whether your architecture's application meets these reliable, frequently changing, rapidly evolving criteria, then we kind of came up with this set of qualities. They're often referred to as the ILITs because they all end in ILITY. But again, they're quite high level, but they kind of make sense, I think. And then we started talking specifically about architectures. And the first architecture we looked at was the monolithic architecture. And I made the point the last day, which was that any server-side applications that you have developed so far in your 3-year undergraduate studies, I'm pretty confident in saying that the architecture of those applications would meet this monolithic architecture style. And I talked a little bit about that. And that architecture is fine for relatively small applications, but once the application size grows, and ideally it would grow over time if it is a successful application, as in it meets the needs of your customer or your client, then that the application is going to evolve and grow over time. Now, initially, the application might have met all of the ilities that we had out there on an earlier slide, but after a while, it starts to break down. It starts to lose its modularity, lose its maintainability, testability, evolvability, deployability. These and scalability as well is a very important quality. So it tends to lose those criteria. And because of that, we then, well, what happened in the industry was a new architecture style came about called the microservices architecture. And essentially, the idea of the microservices architecture is to take your monolithic architecture and break it up into a number of smaller applications. Okay. So each application, if you like, each of these is a little mini application, and it runs on its own node, and it communicates with the other parts of the overall application, communicates with them over HTTP. So now we have essentially broken up a large monolith into a number of smaller, what we call microservices. And each microservice performs, well, it tends to be linked with one particular part of your client's business model, if you like. So it made a lot of sense because as well, what was happening around the time that microservices architecture started to become popular was the whole area of cloud computing started to emerge. And we could now deploy each microservice in the cloud, maybe on an EC2 instance or in something smaller than that, maybe package it as a Docker package and deploy it onto a Docker container that's running in the cloud. So these two kind of came about around the same time. Then the idea was that each microservice now would be the responsibility of a small subgroup within your overall software development organization. And that subgroup was completely responsible for evolving their microservice, if you like. So it made a certain amount of sense. And the underlying hardware, as I said, could support this kind of model. But again, while it started off as being a really nice solution to some of the deficiencies of the monolithic architecture, we kind of finished up in the same problem areas as we did with the monolithic architecture, which is that as our microservices application grew over time, then the amount of communication that was happening between each microservice, that also started to grow. And so the INITY qualities, as in modularity, maintainability, deployability, that started to break down yet again. So the problem that we had is, if I keep going forward now, our microservices architecture started to look a little bit like this, in that there was an awful lot of intercommunication going on between the various microservices that made up our overall application. And so it just complicated things. So now it meant that if a user makes a request, and the request, let's say, first of all, it hits this microservice, but this microservice, in order to complete the transaction for the user, let's say it had to communicate with this microservice, and it had to communicate with, let's say, this microservice, and this microservice had to communicate with this microservice in order to complete its functionality. And so, we just got a kind of a difficult to maintain and difficult to modularize application, difficult to test as well. So the core problem with the microservices architecture was the fact that there was a lot of coupling between, there was a lot of coupling. Trying to erase that. How do I erase it? Yeah. There was a lot of coupling between the microservices. And I think that's roughly where this is where I kind of left off the last day. So this problem of coupling, this has been a problem in programming from day one, whether you're talking about sorry if I just go back. This is essentially, of course, this is now a distributed application or a distributed system, i.e. the title of this module. It's a distributed system, and we've got various compute elements, and those compute elements need to interact or communicate with one another in order to complete some overall user business transaction. So, there's a lot of coupling there, but this coupling introduces some problems. Now, again, let's be clear. Let's supposing we've got this simple example here. We've got these two microservices, and this one looks like, from its name anyway, it handles requests from users to process an order. Yeah. So there is a synchronous request arrives at this microservice to process an order, but in order to complete that processing, it has to communicate with this customer service. Let's say the customer service has to reserve credits for our customer. Customer service completes its work, and then it responds back to the order service, and then the order service responds back to the user to say, I have completed the processing of your order. Now, this communication here, this is what we refer to as, there's coupling. Sorry, we'd say there's coupling between these two microservices, which we can't totally avoid coupling. And the nature of the coupling, or the nature of the relationship between these two, is it is a synchronous relationship. Yeah, as in this microservice has to wait until this microservice has completed its work and responded back before this microservice can continue on processing the user transaction and then ultimately respond back to them. So a coupling, or the dependency relationship, it's called different things. I'm saying it's inevitable, but what we would like to try and maximize is what's referred to as loose coupling, which we'll see how we might achieve that in a few slides. Down here, I'm just saying, okay, there are two types of coupling, but they're kind of interrelated. There's runtime coupling. Runtime coupling is really what I've been describing just there this minute. And then there's also design time coupling. Design time coupling is this idea that if I want to make changes to one particular microservice, then maybe I need to consult or collaborate with some people that are responsible for another microservice in order to ensure that the other microservices that communicate with my microservice, that they all still work together properly. So any design changes that I make to my microservice is somehow dependent on ensuring that the other microservices that communicate with my service, they may need to be upgraded or updated or changed as well. So that's another form of coupling or dependency relationship, which I think I elaborate a little bit on here. So I'm saying design time coupling requires the service team, whoever's responsible for their service, to collaborate with other teams to ensure that the overall application will still work. And what I said about each microservice and the subgroup or the team of people that are responsible for a microservice, ideally, they should be able to work autonomously. They shouldn't have to collaborate with the other teams that are responsible for the other microservices. That's the ideal world. So yeah, we're trying to minimize as well. We're trying to minimize design time coupling. Now, the next slide, okay, it tells us how you might achieve that. Well, it doesn't actually tell you how you might achieve it, but it tells you what you should try and aim for your microservice. It's a nice visual, but I won't have time to get into the detail as to how you might achieve it. And so what the message is trying to get across is that you should design microservices as if they're like icebergs. To relate that from a technology point of view, try to have the interface or the API of your microservice as small and as stable as possible. Now, essentially, this part of the API is kind of the REST interface part of if we assume that our microservices are communicating over HTTP and they're all REST-based services, which would be the case in the majority of instances. But try to keep the RESTful interface as small as possible and define it at the beginning such that it's not going to change over time. It's stable, in other words. Again, that's easy to say, but it may not be that easy to achieve. But at least that's what you should be aiming for. Now, the internals of the microservice, which is represented by the blue part, that's where all the functionality is. And if you've got a small interface that's stable, then that really means that the rest of the microservices, that's all they see. They don't see the internals. So you can happily make any changes to the internals of the microservice without worrying about, is this going to affect the other microservices in my overall application? So that's what you should aim for, a small, stable interface. And then, okay, it doesn't really matter how much changes go on in the internal of the service. That's just now related to design time coupling. If we go back to runtime coupling, which is where I'm going to focus on for the next while. But before I do that, another aspect this image is telling us, another aspect of design time coupling is you should try and avoid situation, or minimize anyway, the situation where you've got a number of services that are using the same database. This is a point I made last week when I introduced this microservices architecture. One characteristic of it, which a lot of people had difficulty with initially, was that each microservice has its own database. There is not one shared database between all the microservices. Because if you've got a shared database, then that becomes the point of conflict, because maybe the team that are responsible for this service, maybe they want to make some changes to the schema for certain tables within this database. But if this microservice is using those same tables, then this service now also has to update its internal workings so that it can still read from the tables whose schema has been changed by the service on the left. So that's coupling indirectly. So rather than shared, split out your databases. That may mean that there is replication of a certain data between these two databases. There's the same information being stored in both databases, and then you have the problem of keeping the two databases in sync, but it's felt that that's a better approach than the shared database. Now, back to the coupling problem, the runtime coupling. And this is linked to the fact that the runtime behavior is really implementing a synchronous interprocess communication. That's the nature of the communication that's going on between my sample two services here. It's a synchronous communication flow. And what that can impact on is it can impact on both the latency and the availability of, in this case, this service here on the left, because this is the one that's contacted by the user or the client side. Client side makes a request to this service here. But because this service synchronously communicates with this one, then that is going to impact on the latency of this service here. Latency is really how quickly does this service respond back to the user. And clearly, it's impacted by this service on the right. Also, I'm talking about the availability. The availability of this service is impacted by the availability of this service. Availability simply means when a request arrives for a service, is the service up and running? Is it accessible from a networking point of view? And we would say that the availability of this service, because this is the one that the client interacts with, the availability of this service is impacted by the availability of this service. And, you know, the kind of formula here is kind of expressing that. So availability and latency of a service, in this case, my service that I'm focusing on is this one here. Both the availability and the latency of this service is impacted by the other service or services that it communicates with synchronously. So can we somehow improve on the latency and availability of this service in some way? The other interesting point just made at the start, at the top of this slide here, and it actually reminds me of something that I see students doing a lot. It's saying here that this distribution, you know, when we moved to the microservices architecture, we essentially broke our application up into a distributed application, as I mentioned at the beginning of the lecture. But that distribution, you know, that doesn't come for free. Because it now means that two parts of your application are now communicating over a network, whereas in the monolithic architecture, they were both running within the same operating system process. And so there, you know, there was no latency and availability concerns there when it was in the monolithic. But distribution doesn't come for free. Now, it's unrelated now to distributed systems, but what I see a lot with students, including me, is that you use OneDrive quite a lot, which makes sense. But I mean, OneDrive is located across a network. You're accessing a drive that's on a network. It's not local to your machine. Really, when you're doing any kind of development work, again, now this point is slightly off topic, but I'll make it anyway. When you're doing any development work, you should really be doing development work on files that are on your local machine. And then by all means, make backup copies on OneDrive or up on GitHub or wherever. But editing files that are actually located on the OneDrive is probably not the best way to go as in your day-to-day development. Anyway, that's kind of off topic, as I said. Let's go back. Let's come back to the microservices architecture and the fact that breaking an application up into microservices has consequences, and the two consequences are what I've been talking about here. So the solution to the problems on the previous slide are to change from synchronous communication between my two processes, change to asynchronous communication, if possible. That's an important caveat. And let's assume that it is possible in this case. So what we now do is we still have our two processes here, our two services here. But now when this service receives a request to process an order, the service it puts it communicates with the service on the right via some sort of middleware, and in this case, it's messaging middleware. So whatever information this service needs to pass to the service on the right, it's actually going to put that information. Let's say it's a JSON object. It could be the entire order JSON object. It puts it into some sort of messaging middleware. And the service on the right, it will pick it up from there, do its processing, and when it's finished, in order to communicate back to the service on the left, it will put a response into another message middleware queue, actually, as it turns out. And this service picks it up and responds back accordingly. Now, just bear in mind now that when the service here on the right, it actually polls this queue here. It polls it periodically, checking to see, are there any messages on this queue that I should process? Don't get the impression that when this service puts a message onto the queue, that straight away this service is triggered. That's not how it's meant to happen. If that was the case, then we're kind of back to synchronous communication between the two services. The way it works is this service puts some message onto this queue, and periodically this service checks the queue to see are there anything there. So there will definitely be a delay between the time the service on the left puts the message onto this queue and the service on the right actually picks it up. There is a delay there. Equally, when the service wants to communicate back to the service, there's going to be a delay because this service here now is going to be periodically checking this queue to see are there any messages that I should process. Also, when the original request comes in from the client or the user, the original post request to submit an order, this service can respond back to the client, but of course it's responding back now before the service on the right has completed its processing. And so when the service on the right does complete its processing and puts a message into this queue, and this service picks it up, maybe this service communicates for a second time with the client to some effect. So the first response from this service back to the client might be, I have received your order and it is being processed. The second response from this service back to the client would be along the lines of, your order has now been fully processed. Okay, so that's a consequence, obviously, of changing from synchronous communication, which we had on the previous slide, to this asynchronous communication. And it may be for a particular use case that isn't good enough. We need to go back to synchronous communication for this particular type of transaction. And you have to kind of deal with it on a transaction by transaction basis as to whether asynchronous communication will suffice. But for sure, the introduction of this middleware here does solve the problem of the availability of this service. Now the availability of this service is not dependent on the availability of this one. Because again, if a request comes in, a post request comes in, this service does some preliminary processing of it and puts a message onto this queue here. Let's supposing this service is currently down or it's inaccessible. The node that it's running on is in part of the network that's currently inaccessible. That doesn't affect this service here. It can still, once it's put its message onto the queue, it can still respond back to the user to the effect, I have received your order and it is currently being processed. Later on, the network that this service is part of is now back up and running again. This service will now check to see other messages in the queue, and it'll get the message and process it, etc., etc. So my service here on the left is no longer impacted by the service on the right in terms of the availability of this service. Also, arguably, the latency has been improved because now this service can respond back much quicker, much more quickly to the client, because it's not waiting for the service on the right. Now, again, there is the caveat though that the response back to the client is not the same as the kind of response that we had in the synchronous case. So what we want to look at over the next couple of weeks is how to, on the AWS platform, what are the different AWS services that facilitate this kind of message broker architecture. This then is kind of the big picture of where we're going with this. So, and I found this image somewhere on the web, and now there's a little bit too much information on it for us, but it's a nice, I thought it was a nice kind of visual representation of what we're aiming for here. The title that I've given this slide is that we're still talking about microservices, the microservices architecture, but it's the microservices architecture where you've got predominantly asynchronous communication going on between the microservices. As you can see here are my microservices. You can just ignore the stuff on the left here for the moment. Here are my microservices. Sorry, here are my microservices. They all have their own database, and they are communicating with one another via this messaging piece of infrastructure. Yeah. All the stuff going on over here on the left is, just to complete the picture, if you like. You could well have a mobile client and a web client. Maybe the web client is broken up into a number of websites. Those websites, web apps, really, I guess. This could be a React app. This could be another React app. This could be an Angular app. They're communicating with services synchronously. Equally down here, you could have a mobile client. You could have an API gateway. We know what that's about. And both the website and the mobile native are using the API gateway in order to communicate with the microservices. Again, this communication here is synchronous. So this communication here, if you like, is equivalent to this communication here. But it's this red box on the right is what makes this architecture more asynchronous in terms of the communication that's going on between the microservices. And the name we would give this kind of architecture is what's called the event-driven architecture. I won't go into where that name is kind of coming from now, but that's when we talk about event-driven architecture, we're talking about asynchronous communication going on between the various microservices in a microservices architecture. Okay, that's enough of kind of high-level stuff. And I want to go back to AWS specifically. So if I go back to my website, we've got a new section here on messaging. And there will certainly be a lab in this section, but I decided to leave the lab out for this week so that you can concentrate on the assignment. So I want to start looking at these slides here. And really, it's going to take us a number of weeks to get through all the stuff that I want to get through here. It may take us well up into the end of the semester, if truth be told. So let's start looking at these slides. Can I confirm that you can see my slides again?
Yeah, we can see them.
Okay, so we're back to AWS, and it's I've titled AWS integration, as in how do you integrate different parts of your application, I guess, and specifically using messaging. And this is going to be what's going to enable us to develop event-driven architectures, albeit kind of small architectures. This is a slide we've seen a number of times. We're still kind of in the serverless model, but what we're adding to the serverless model, because the serverless model, arguably, that we've been looking at so far, is all based on synchronous communication. But we're going to add in some message-driven aspects to this, and collectively, then when you bring message-driven and kind of serverless together, that's what we are now calling this event-driven architecture, or EDA for short. And we are going to look at two services that enable this event-driven architecture, and they are SQS and SNS, which are these two guys down here. Now, we hardly need reminding, because I've just been talking about it for the first part of this lecture, but the whole reason why we need these two new services is synchronous communication between microservices can be problematic, and I've elaborated a lot on that so far. By the way, I'm actually also saying here is it's synchronous communication between monoliths. Like, this problem of synchronous communication was also an issue back in the days of the monolithic architecture, because what you could have is two or many monolithic architecture applications that actually also wanted to communicate with one another. You could imagine one organization's application wanted to communicate with another organization's application, because those two organizations carry out some business transactions between them. So their software applications also need to communicate. And even if those software applications were based on the monolithic architecture, how do we enable those two monolithic applications to communicate with one another? One way would be that the two applications would have RESTful interfaces, and that would work. But if they're communicating across RESTful interfaces, then that's essentially synchronous communication, which we don't like. But how can they communicate asynchronously? And so these two services, SNS and SQS, they can also be used to allow monolithic applications to talk with one another. It's not unique to microservices. So it's better to, decoupling is another term I'm sure that you've heard before, but this term decoupling is really what we're talking about. We're trying to decouple microservices from one another. So the services, as I said, that we're going to look at are SQS, which stands for Simple Queue Service. And it's a way of allowing two microservices to communicate in a kind of a point-to-point model. So they're just concerned with communication between two services. SNS, which stands for Simple Notification Service, that allows a kind of one-to-many type communication, or the technical term is a pub-sub, a publisher-subscriber asynchronous communication model. There's also something called data streams, which I'll talk about really at the kind of the back end of this section. It's about enabling asynchronous communication, but it's kind of indirect as opposed to these two here. So we'll just park that one for the moment. And the other answer as to why we are interested in decoupling our microservices is for these good reasons down here: to reduce latency, increase availability, reduce tight coupling. So let's look at the SQS service first, which, as I said, stands for Simple Queuing Service. Now, at a very high level, where this is used is if you've got two components, let's use a generic term. The components could be two monolithic applications. They could be two microservices. They could even be two lambdas. And in our case, that's what we will be using as our components. But one of the components is termed the producer. It's the component that's writing messages into our queue. This is representing our SQS queue. And we know what a queue is from general computing, okay? And then the other component we refer to as the consumer. It's only concerned with reading messages off of the queue and doing some processing of them. Okay, so we've got the producer, the consumer, and we've got the queue in between them. This is probably closer to how we will see this SQS service being used. So we have our API gateway, which we know about. We've got a Lambda, which is triggered as a result of a request coming in from a client. By the way, the communication flow here is synchronous. We can't avoid that. But let's say whatever processing this Lambda does, it needs to also ask this Lambda over here to do some processing as well of the client's request. But we've decided that we want to break this link rather than this Lambda talking directly to this Lambda. We're going to use an SQS queue in between them. The implication also is that the request that comes in from my client side, it's important that that request is processed by this Lambda, but the client doesn't need to wait for the Lambda on the right to complete its processing. It does not need to wait for it. If it did need to wait for it, then using the queue here isn't going to work, right? We have to go back to synchronous communication between the two. But if it's the case that whatever processing this does, the client does not need to wait for that processing to complete, that's when you decide, I'm going to introduce a queue here in between these two lambdas. And I've already made the point, but we'll see it a little bit. I'll repeat it again later on, maybe, is that this lambda is going to be writing messages to the queue, but the messages may remain there for a short period of time, whatever short is or whatever. But for a period of time, they will be in the queue for a period of time before this lambda actually processes them. And the reason for that is this lambda, it just periodically checks to see, are there any messages in the queue? It's not triggered straight away when a message is put on the queue. Okay, so we've got producer. So we would say this is our producer lambda. This is our consumer lambda. This is our queue in the middle. Bit of history. It turns out that the SQS service is actually the oldest service on the AWS platform. So it predates Lambda, DynamoDB, serverless, predates all of that stuff. And its original use case was for what I was talking about earlier on, where you had two monolithic applications that wanted to communicate with one another asynchronously. That's why Amazon provided this SQS service. That's just a by the way. For sure, today, the SQS service is predominantly used in the context of serverless applications. It's a fully managed service. That's now a byword for saying that it's serverless. We don't have to configure any servers to run to manage our SQS queues. We don't have to do that, but for sure, there are SQS servers that are responsible for managing the queues. It's a distributed, our queues are distributed. I'll come back to that in a moment, in a few slides. And it's used to decouple application components. That's fine. So fully managed now means, as I said, we don't have to actually configure any servers to manage our queues for us. The attributes of the SQS service and implicitly kind of the attributes of an SQS queue. It's unlimited really in terms of how many messages you can put into the queue. It is almost unlimited, there can be any number of messages building up inside in the queue. There's unlimited throughput of the queue. In other words, the reading and writing that goes on, and that can be going on in parallel. There is a certain amount of persistence provided by the SQS service, as in messages can remain in the queue for a period of time. It's not like a database, but the default is that messages can remain in a queue for 4 days. And that's really to facilitate the possibility that the consumer services, the consumer components are, they're not available, or they have crashed temporarily. Okay. Maybe the availability might be due to network reasons. And once the consumer service becomes available again, once the consumer component becomes available again, then it can check to see, are there any messages in the queue, and it can pick them up and process them. So the SQS service will persist messages for up to 4 days, but you can configure it so that it can live longer in the queue. But certainly it's not a database as such. You can't persist them for months or years or anything like that. Low latency. So, when you write to a queue, you'll get a response back within less than 10 milliseconds, confirming that your message has been written to the queue. And from the consumer side, when it tries to read a message from a queue, then the AWS people guarantee that if there are messages on the queue, then it will receive them in less than 10 milliseconds. Okay, it's kind of a ballpark, but there is a limit to the size of the messages that you can put on an SQS queue, but there are ways of getting around that. But the actual initial default is 256K. Caveats. Okay, it is when you read the documentation on SQS, it does says that it is possible that the consumer may receive the same message more than once. So there's no guarantee that there will not be duplicates of a message received by the consumer. However infrequently that may happen, it is a possibility. And because it is a possibility, you have to take that into account when you're implementing your consumer component. In other words, your consumer has to be idempotent. Secondly, we're told that the messages are not essentially in order. Down here. The messages aren't received in the same order necessarily than the order in which the messages were written to the queue. If order is important in a particular application, then you can configure the SQS queue such that it maintains the ordering of the messages, but by default it doesn't. And we may see that actually in practice when I do some demonstrations. So this duplicates and this ordering are the two aspects of queues that you just need to be aware of as the developer of the consumer component, because that's who it impacts on. The basic operations, fairly predictable. I guess from the producer's point of view, they publish or write messages to a queue using the SQS services SDK. So the SQS service, like every other service, provides an SDK to allow components to communicate with the service. We're told that messages are persisted. I've kind of already made that point. Am I elaborating? Messages are persisted to queues until a consumer. Oh yeah. It is the responsibility of the consumer to delete a message from a queue when it has processed it fully. So that is the responsibility of the consumer. The SQS service itself doesn't deal with deleting messages from a queue. So if the consumer never deleted messages, then the queue would just start building up and up and up and up, and messages would never be removed. So that is an extra responsibility on the consumer. Although there is a caveat, and the caveat is that when a message is placed on a queue, that message has certain attributes associated with it. One of the attributes is its TTL, its time to live. And so that would be set by the producer, the component that writes the message. It would set the TTL of a message. And we know how TTLs work. In this context, it means if no consumer processes the message within the TTL time limit, then the SQS service in that case will actually delete the message. So I was kind of slightly misleading you there at the very beginning, but so TTL is the kind of safeguard to ensure that messages don't remain in a queue, forever. On the consumer side, the consumer kind of already made this point. The consumer polls the SQS service. It periodically asks the SQS service, are there any messages in a particular queue? And if there are, then the SQS service will return those messages to the consumer as a batch. Okay. And the default batch size is 10. Now, again, it's always going to be a batch. Even if there's only one message in the queue, the consumer has to treat the response that it gets back from the SQS service when it does a polling. It has to treat the response as if it received, well, it has to treat the response as a batch of messages, even if there are only one entry in that batch. And again, you'll see that when we program a consumer in Lambda. Process messages, well, the processing of a message from a queue by the consumer could involve anything. Typically involved maybe doing some validation of the message, storing something in a database, or whatever. That can be anything. And I've already made the point that the consumer is responsible for deleting a message from the queue once it has processed it fully. And so the image here is kind of reinforcing this idea that it's a batch that is passed to the consumer by the SQS service when the consumer polls the service. Security is always an issue with Amazon, and there's two aspects. First of all, well, there are a couple of aspects. First of all, encryption is utilized fully by the SQS service. And there's two aspects to encryption: in-flight encryption and at-rest encryption. By in-flight encryption, we mean, if I just go back to here, let's say, what the SQS service will do is, well, if we, let's say, take this one down here, the communication here is over HTTP. The communication here is over HTTP. So it's traveling over a network, but the SQS service will perform encryption on that traffic. So that's what we call in-flight encryption. Also, we know that the messages are stored in a queue. They're persisted there for a period of time, and they are persisted in encrypted form. So they're never in plain text. So that's one part of security from in relation to SQS. And of course, IAM plays a role as well. So any component that wants to interact with the SQS service, whether it be for the purpose of reading or writing to an SQS queue, then that component has to have the relevant IAM policies, permissions to use the essentially to use the SQS SDK. And the third aspect of security is if you want to have a queue that can be accessed by other accounts, other AWS accounts, then you have to kind of configure that aspect of your queue. Also, it's not just lambdas, for example. It's not just compute components that can write messages to a queue. Non-compute components can do it as well. For example, the S3 servers or DynamoDB, they can actually also write messages to a queue. We'll see later on how we can get S3, the simple storage service, how to get that, how to configure that to write messages into a queue. Similarly well, we haven't looked at the SNS service, but the SNS service can also write messages into an SQS queue. But those other services, they will only be allowed to write messages to a queue if you have configured the queue's access policy to so do. Now, let's get to some examples. Simple example, the simplest one I could come up with. So I'm going to have an SQS queue, and I'm going to be writing to the queue using the AWS CLI. So essentially, the AWS CLI is going to be communicating with the SQS service for the purpose of writing messages to this queue. And on the consumer side, I'm going to have a Lambda that is periodically polling to see if there are any messages in this queue that it can process. And all it's doing really is console logging the messages. It doesn't do any processing as such. And so the text down here is saying that the Lambda service, here's the Lambda function that we write, but the Lambda function uses the Lambda service. It's the Lambda service that actually does the polling of the queue. It's not the Lambda function itself. So the Lambda service periodically polls the queue, and if there are messages, then the messages are given to the Lambda service, and the Lambda service then passes the messages to the Lambda function within the event object that's available to this Lambda function. This communication here is actually synchronous, between the Lambda service and your Lambda function. So again, without at the risk of repeating myself, it's actually the Lambda service that takes care of polling the queue, receiving the messages from SQS, and then passing them to the Lambda function. The Lambda function itself does not communicate directly with SQS. Also, so the Lambda function here, or Lambda handler, it receives a bunch of messages from the Lambda service. It processes them, and provided it does not throw an exception, in other words, it processes the messages successfully. If it completes successfully, then the Lambda service automatically deletes those messages from the queue, because we did say that the consumer is responsible for deleting messages from the queue. So the Lambda service will do that deleting for you. You do not have to put any code in your Lambda function to take care of deleting messages from a queue, which makes our programming model a lot cleaner, really. And so that's what I'm talking about down here. If the Lambda function throws an exception as it's processing messages, in other words, it has found a problem with one of the messages. If it throws an exception, then the Lambda function, sorry, if it throws an exception, then the Lambda service, it's not going to delete the messages at all. They're still going to be there. Yeah. And I think that's what I'm saying down here. If the function processing, if the function processes the entire batch without throwing an exception, okay, the Lambda service deletes the batch. That's fine. Otherwise, I'm saying down here, otherwise the entire batch is reinserted. Well, it's not so much as reinserted, but they're not actually deleted. Reinserted in the queue for subsequent processing. So it's possible that this Lambda function here may receive the same batch of messages a second time when the Lambda service polls the queue again. Maybe the reason the Lambda handler threw an exception is because it timed out, right? It's not so much that there was a problem with the messages themselves. There are a number of reasons why the Lambda function may not complete. Okay. So can I show you? Okay, so here's some excerpts from this little mini application. So from the CDK point of view, how do I create an SQS queue? It's a simple one-liner. Okay, so that's just creating a queue for myself. And I'm not doing any specific configuration of the queue. So I'm accepting all the kind of defaults like 4 days. Messages can remain in the queue for 4 days, plus lots of other configuration settings. Later on, we will do some configuration of our queue, but it's that's how you create an SQS queue. Here I've just got a Lambda function, and from the name we can tell that this is the Lambda that's going to be processing messages from the queue. And it's this bit down here. This is how we form the connection between my Lambda function and the queue. So we create what's called an event source. Like one of the points I made about the Lambdas when we were talking about them way back is that Lambdas are triggered by some event occurring. Now, that's really kind of what we're setting up here. We want our consumer Lambda to be triggered when messages arrive in my SQS queue, or more specifically, when the Lambda service, having polled the queue, receives some messages from the queue. That's what's going to trigger my Lambda. And that's essentially kind of what I'm doing here. I'm first of all creating what's called an SQS event source, which is linked to my queue. And then I'm kind of attaching that event source to my Lambda function. And I'm just outputting the URL of my queue because I need that in order to allow my AWS CLI to send messages to the queue. So I guess this part here is kind of and this line here is what's new. Here's the consumer. And again, it's a Lambda. Okay, its type is slightly different, although that's not really significant, right? It's an SQS handler. Here's the event. Always the Lambda receives as the first parameter, it receives the event, but it's inside in this event object. When we look inside the internals of the event object, That's where we will find the batch of messages that has been retrieved by the Lambda service from the queue. And so that's why here I'm actually, okay, I'm just console logging the event, which is always a good idea. But then I'm going into a particular part of the event called the records property. And that's only going to be there if this event is linked to an SQS queue. The records property, that's going to be an array, i.e. my batch of messages. So that's why I'm looping over this array. And each time through this loop, I am going to be this record variable is going to refer to one message, and I'm just console logging the message. I'm not doing anything interesting with it. And down here, I'm showing you how to communicate using the AWS CLI with a queue. Now, so I've deployed. So if I go over to VS Code, here's the different parts of this little project. Here's my CDK stack code, which we've already talked our way through that. Sorry, that's incorrect. Close that. Here's my stack file. Yeah, my queue, my Lambda, and hooking the two up. And I'm just outputting the URL of the queue. So when I deployed this stack just before the lecture, let's see. Okay, here's the URL of the queue. A queue does have a URL to facilitate because it's all we're communicating with it over HTTP. So the line that I've highlighted there is as a result of this statement in my CDK stack. And my consumer, well, I kind of already shown you the consumer. Here's the consumer, and it's not doing anything interesting other than just looping over the messages and console logging them. You can forget about this for now. It's not important for now. So let's send the message to my queue, I guess. Before that, if I switch over to, let's clean up CloudWatch logs. Looks like it's already cleaned up. And let's send the message. So if I go into my README, this is how you send a message. So I just need to change the URL here. So my message is just a simple string. Okay, this is the response that's coming back from the SQS service. So that doesn't tell us anything that useful other than each message it gets its own unique identifier. And that's what we're getting here. So this is a unique identifier for a message within the entire global kind of SQS service, if you like. And if I switch over to CloudWatch and do a refresh, so let's see now. There are two of them there. This is the log group that I'm interested in. I'm not sure for now where that log group is coming from. Let me just, I'm just going to clear off this again. Sorry, now. And I'll send a message again. Okay, so as I expected, only one log group, which is the one linked to my consumer Lambda. And if I drill down into that and go into the log stream. So in my consumer Lambda, I have a console.log statement at the beginning. And so let's look at the detail of the event object that's received by this Lambda. It's going to be different from the structure of an event object that would be received by a Lambda when it's triggered by API gateway. So if we look inside it, and it's in the, here's the records property of the event. And I mentioned to you that the records property within the event object, that's going to be an array or a batch. And we can see that that's true here. And it's going to contain a batch of messages. Now, there is only one message, so this is my entire message here. Where does it end? This looks like being an entire message. And the only, for now anyway, the only important part of the message is the body of the message. And lo and behold, here we've got hello world, which was the message that I sent to my Lambda. Okay, so that's kind of the 101. And there isn't much else we can say really about that. So if I go back to my slides. That's just confirming what I saw in CloudWatch logs. So that's all right. Now, typically a message is going to be, it's the kind of the payload of a message is going to be a JSON structure. In the majority of cases, it's not going to be something as trivial as a string. So there's just one or two things that you need to be aware of when a message is a JSON structure. And so to illustrate it, let's supposing this is a simple JSON structure that I want to send into to write to my queue, and I want my consumer Lambda to process it. First of all, if you want to use a CLI to send a JSON structure, then it's slightly different in that, well, you can hard code the JSON structure in the invocation, but a neater way would be to put your JSON structure into a file, which I've done here, and then this is how you actually refer to the file. You use the file protocol to refer to it in the AWS CLI command. And I think, do I have that? Let's see, do I have that file available to me? So let's supposing here we go. Here's my simple JSON file, and let's use that command to talk to. So slightly different. Here's an example of it here. So if I just delete, I need to change the URL because that's an older URL that I was using. What did it like? Not sure what it doesn't like there now. Anybody see what I'm getting wrong? Okay, let's do this. Okay, it's a bit better. Let's go back to CloudWatch logs. Back to my log groups. Here's my log stream. And if I expand the event itself, which is this one here, and point I want to get to is here. So because it was a JSON structure, let's see. Sorry, that's the wrong one. Should be looking at this stream. Here's the body of the message, and the point I want to get to is that the JSON structure is it's stringified. Okay, it's converted into a string. That stringification is done by the SQS service itself. But this is what the consumer, Lambda in my case, this is what it receives. So it needs to, first of all, parse the body of a message before it can process it in a meaningful way. And so if I now go back to my slides, okay, this is what you need to do. So this line here is kind of important. I'm parsing the body of the message, and then I can process it. That's the only point there that you need to be aware of. What am I saying down here? Note the Lambda handler does not. Oh yeah, I kind of, well, I have mentioned it, but you may have missed it. The actual Lambda function or the Lambda handler, it does not explicitly read from the queue. Like there's no code in here which involves my Lambda using the SQS SDK to talk to the SQS service. So this Lambda doesn't need any privileges, any additional privileges. Yeah, because it's not actually communicating directly with SQS. The Lambda service, okay, the Lambda service does need privileges in order to poll the SQS queue, but we needn't worry about that in terms of our infrastructure code. Right. Just to move away from the coding side of it for a moment, this is an image that I grabbed off of the SQS online documentation, really Amazon's own SQS online documentation. And when I started talking about the SQS service, I said that if I just go back to it actually, to here, see, I said, where did I say it? Yeah, I said that it's a fully managed, which is fine, but I said it's a distributed queuing service. Now, it turns out that when you create an SQS queue as part of your application's infrastructure, what the SQS service does is it creates a number of duplicate copies of that queue. And again, this is to guarantee that the queue is always available. Availability is a really important characteristic when you've got applications deployed to the cloud, that the queue is always available to your application. If there was only one copy of the queue uh, sitting on an SQS server, and that particular server, for whatever reason, was inaccessible from a networking point of view, or if the actual server had temporarily crashed, then your queue is not available to the consumers while that situation uh, pertains, and that's not good, right? So for that reason, there are duplicate copies of your queue, and those duplicates are spread across the global AWS. Well, it's more on a regional basis, really. They're spread across the different availability zones of the SQS service for a particular region. And that's what I'm getting at in this slide. So let's say, for example, we've created a particular SQS queue in a region, and what SQS will do is it will make multiple copies of that queue, and each copy is being managed by an SQS server that's running on the same node that the queue is actually persisted on. So it looks like, just for this example, it looks like there are 1, 2, 3, 4, 5, 6. Is it 2, 4, 6, maybe 7? 2, 4, 6, 7. That there are 7 SQS servers running across whatever region we're looking at here. And each SQS server has not a full copy. It actually has a copy of part of our particular queue. For example, if we look at the detail, let's supposing the messages in our queue are just A, B, C, D, and E, I think. It looks like this particular node, SQS node, has a copy of message A and message D. This one has message B, C, and D, and so on for the other ones, right? So there's a degree of replication of the messages across these different nodes. Each node is not a complete copy. that would be overkill as far as AWS is concerned. So it's distributed anyway. And just the color coding that's used here, let's supposing that it's only this one, and this one. These three SQS servers are available. For whatever reason, the other SQS servers are not available in this particular snapshot of the region. Over here on the left, then I have consumers. Now, let's forget about the fact that there are multiple consumers for the moment. Let's assume that there's only, one consumer, which is my Lambda. So we'll just scratch these out. And when this Lambda, via the Lambda service, polls the SQS service, then what the SQS service does is it will select a subset of the nodes. And let's suppose in the subset that it has selected are these gray ones. Sorry, I said there a moment ago. Let's assume these ones are unavailable at the moment. Let's assume all the nodes are available. Okay, so they're all up and running. But when the consumer, in my case, the Lambda service, when it polls a particular queue, then what the SQS service does is it selects a subset based on an algorithm. It selects a subset of the nodes and it checks to see the messages in those nodes. So if supposing for this snapshot, it selected this server and this node, then based on the messages that are being stored in the queue on those particular nodes, then it will respond back with message ACDB. Now, why they're ordered that way is not important, but it's only going to return those messages because they are the only ones that are available in the nodes that have been kind of randomly selected by the SQS service to check to see for the existence of messages. Yeah, so I'm saying down here, when a consumer polls for messages, the SQS service samples or selects a subset of its servers, and that selection is based on some sort of weighting algorithm. We don't need to get into the details of that. And it returns the messages from that subset only. And what's the whole point of this kind of replication? It is to ensure that the SQS service is, I'm saying here, it's resilient. It's resilient to failures in the network, and failures would materialize as certain nodes not being available when a polling request has been received by SQS. Why they're in this order isn't really clear. Why they're in the order ACDB and not ABCD. That's not really can't really work that out from the screenshot. And we're told that anyway from the SQS documentation that you can't be guaranteed that the messages are received in the right order. Okay, so that's it's slightly just moving away from the nitty-gritty of how we use the SQS service to talking a little bit about how it works behind the scenes. In terms of scalability of our consumers, because if there is a very high volume of messages being sent into the queue, then we'd obviously like those messages to be processed as quickly as possible. So if when the consumers are Lambdas, then the Lambda service itself will take care of scaling up as many copies of the Lambda function as it needs to deal with the volume of messages that it is receiving from the SQS service when it does its polling. So I'm saying that the Lambda service Okay, we know it polls the queue for messages. We know that already. Messages are passed to the consumer. We know that as well, I guess. But from a scalability point of view, I'm making the point that down here that the Lambda service it instantiates. Well, what the documentation says is it instantiates 5 instances of a function at the very beginning. So it creates at least anyway a number. It may not necessarily be 5, but it creates a number of copies or instances of your Lambda function before it ever starts polling for the queue. Now the documentation says it creates 5 of them, kind of arbitrarily decides on 5. But it's difficult for me to prove that to you. But either way, it creates a number of Lambda instances in the anticipation that when it does poll the queue, that it will get a large enough volume of messages that it can distribute it between those Lambdas, which will process them in parallel. So my Lambda service, it has created a number of instances of the Lambda function handlers or consumers. Then it polls the queue. It receives a batch of messages, and it won't give the entire batch to one Lambda. It may actually split the batch up and give some of them to one Lambda, more to another Lambda, and so on for the others. And it lets them do its processing. Now, while those Lambdas are processing, my Lambda service will, at some stage in the immediate future, poll again for more messages. And it's supposing it now receives another batch of 10 messages. But my Lambdas are still processing the messages that were received from the first polling. Well, the Lambda service won't wait for these Lambdas to finish executing. It will actually spin up some more Lambda instances and pass the second batch to those Lambda instances. So it's doing that scaling automatically for you. And the detail is down here. I'm saying for very high message volumes, and this is taken straight from the documentation, the Lambda service could potentially spin up to 60 instances of your consumer Lambda. And it will do that up to a maximum of 1,000 instances if it needs to. And that 1,000 is, if you remember, that 1,000 limit is dictated by the fact that no AWS account can have more than 1,000 Lambdas running at the same time. So potentially, if you've got an application that has a Lambda function that is linked to a queue, potentially you could get up to 1,000 instances or copies of that Lambda running in parallel as a result of high volumes of messages coming into your SQS queue. But the overall point is that the Lambda service, it will take care of this scaling up for you. You don't have to do anything in your code. You can control it to a certain degree. You can put an upper limit on how many parallel instances of the Lambdas can be spun up, and I'll show you how to do that. And it would be a wise thing to do in the real world. But the Lambda service will take care of creating the parallel instances for you. Just checking my watch for time. Okay. Here's just another scenario that I've just kind of put together. So in this scenario, I've got a Lambda that really this Lambda here on the left is acting as a kind of a test harness. So it's generating messages, and arbitrarily the messages are kind of orders, let's say. It's generating messages and it's writing them via the SQS service into my queue. And again, on the right, I've got a consumer Lambda that's reading those messages and processing them. Again, the processing doesn't involve anything interesting. So this Lambda here now, because it's writing to the queue, it will need permissions to do that. And, that's a simple one-liner statement, which is a bit like when you've got a Lambda that wants to write to a database. So there's this convenience function available to us called, in this case, grant send message. So that's how we give a Lambda function the permission to write to a queue. Of course, that translates into some sort of IAM policy that's generated dynamically behind the scenes. We can look at that maybe later on. Down here, I'm showing you an excerpt from the CDK code. And again, what we're doing here is, this is linked to the consumer now. We're adding, for this Lambda over here, we're adding an event source to the consuming Lambda, which, the event source is linked to my SQS queue. But here I'm actually setting some configuration settings. Well, one of them has been commented out, but this configuration setting here is controlling how frequently the Lambda service should poll the SQS service for messages. And I've just arbitrarily decided that it should poll every 10 seconds. The second configuration setting, which I've commented out for the moment, this is how you control the number of parallel instances of your consuming Lambda that you're allowing the Lambda service to spin up. So I've just, in this one, when I will enable it, I'm telling the Lambda service, you should never have more than 2 instances, parallel instances of this particular consumer running at the same time. Here's the Lambda that's actually writing messages to the queue. So what I did was I just hard-coded an array of objects. So these are my order objects now, my order messages, but they're really just JSON objects. So I've created an array of them. Don't worry about the types here. I probably should have left that out actually, because later on what we'll do is we'll put some bad orders or invalid orders in this array. But for now, let's assume it's an array of all valid orders, valid in the sense that they're structured properly, right? And here's the code for writing messages to a queue. So in this case, what I'm doing is I'm first of all creating an instance of my SQS client. So this is the first case now where we're using the SQS SDK. So I'm creating an instance of my SQS client. And the way you use the SQS SDK, bit of a mouthful, is similar to the way we use the DynamoDB SDK. It's all based on these kind of command objects that we create. But in the case of SQS, what we want to create is a send message command. And what are we doing here? Oh yeah, so the parameters that I want to create here. So let me just check now. Okay, no, sorry, I'm just creating an array of these. Sorry, what am I doing? Oh yeah, I'm creating an array of these send message command objects. And so I'm just iterating over my orders. This is the orders over here. I'm iterating over them, and I'm creating an object structure that consists of an order. So I'm stringifying. I think I might have said earlier on that SQS does the stringifying. It turns out that the producer has to stringify the message before it writes to the queue. So I'm stringifying my message. And also each message has to have a unique identifier. And that's what I'm doing here. V4 is just a third-party library that I would have imported at the beginning of this file. It's just a third-party library that will generate unique identifiers for me, so that I don't have to kind of concoct them myself. So it looks like each message, because this is an array of messages, each message as a minimum has to have two properties, an ID property and a message body property. So this array now is set up. Now, for this particular example, I'm not writing one message. I've decided I want to write a batch of messages. And so to do that, I need to use let's see. See, what am I doing? Okay, I'm sending a send message batch command instance. And I'm passing the structure that I've created up here. So it's a little bit like I said, it's a little bit like how we talk to DynamoDB. Now, hopefully SQS this is essentially my reference to the SQS service. It comes back with a successful write operation. And then I'm just returning some default kind of message back to my client, which in my case will be I don't think that goes to anything useful actually, as it turns out. Okay, so that's my producer. And the consumer. Okay, I'm using that HAV third-party library, which you've already seen. I'm using that to validate the order objects within my array. And again, I'm iterating over the array of messages. I'm checking to see, is it a valid message structure after I've parsed the message. Now, I'm throwing exception if it's not a valid structure. And I have the question over here, like, well, who actually catches this exception and deals with it? For now, nobody, but it is going to be important for us to deal with the case where my consumer throws an exception, and we'll see about that in a couple of lectures' time. And then, I process my order, assuming it's a valid order. Unfortunately, we're not going to get to see this working. Okay, so it's bad timing on my part now, but I'm going to have to freeze it there for today. And next week, we will look at running this example and examining the CloudWatch logs, because we will see evidence of the scaling that I was talking about, the scaling of my consumers. And also we'll see evidence of the fact that the messages, orders in my case, won't necessarily be received by the consumers in the same order that they were written into the queue. So that will kind of confirm that ordering characteristic. Okay, so I'm going to leave it at that for today. So for this week, you're going to be working on the assignment still, and that's what I will deal with in the labs on Friday if you've got any questions on it. I'll pause for questions for now, but probably won't be any. Okay, I'll leave it at that, and I'll talk to you later in the week. Bye-bye.
Thank you.